All right, so today we are going to talk about density, significant figures, precision versus accuracy, and dimensional analysis. So the first thing is density. Here we have a glass cylinder containing 4 liquids, and they are all at different densities. 2 have been identified. So the 2 that have been identified are water and mercury. These are all at 25 degrees Celsius. From the list, select a substance for liquid 1 and liquid 3. Explain why. And for the remaining substances, the reason they were not selected. So first of all, let's kind of go through what we know. What is the density of water? 1. So 1 gram per mil. And what's the density of mercury? 13.5 grams per mil. What else do we know about water? This tells me a lot of information. It tells me density, but it also tells me what? It's polar, okay? We know that water is polar. All right, so looking at our liquids, what possibilities could liquid 1 be? What could liquid 1 be? Is it going to be lighter or heavier than water? Lighter. So liquid 1 could possibly be hexane, or it could be ethyl alcohol. So which one is it? Why is it hexane?
It's non-polar, otherwise it would mix with.
All right, because it's non-polar. Otherwise, it would mix with water if it was polar. So liquid 1 has to be hexane. So the next one, liquid 3, it has to be between, the density has to be between water and mercury, and that leaves us with dichloromethane, aluminum, and bromine. And there's a mess up on here. On dichloromethane, where it says nonpolar, cross out the non, because it is polar. All right, so tell me, what is liquid 3? Bromine. Why do you say it's bromine? Because it's nonpolar. Which means that it's not going to mix with water. Why can't it be aluminum? It's a metal, which means at room temperature, it has what? It is a solid. Okay, so that's why we didn't choose aluminum, because it's a solid. And then dichloromethane is polar, which means it would mix with water. Any questions over that? So you kind of have to look at it and break things down to what we know. Oh, dang. Okay, accuracy and precision. So somebody review me. What is to be accurate? If you're accurate, what is it? Yes. As closest to the goal as possible. And what about precision? Yes.
To be as close to your other tries.
Okay, to be as close to your other tries. Your spread, to take your spread and make it really close together. Okay? So looking at these 3 targets here, which set or sets are precise? B and C. Good. Which is accurate? C. And which are both precise and accurate? C. Good. So last night in your reading, you should have read about exact numbers and inexact numbers. So can somebody tell me what is an exact number?
An exact number is a countable quantity.
A countable quantity. Yes, thank you. So this is a counting number. And it has unlimited number of sig figs. It goes on and on and on and on and on.
So digits.
Yes, limited number of digits, yes. And what about an inexact? Somebody tell me another name for an inexact number. Something that is rounded, or so that could be called a measurement. Okay, so when we go into the lab and we do take density, or not densities, but take masses or take volumes or something, it is an inexact number because it's a measurement. We always guesstimate one over than what we're looking at. Okay, so tell me, is it exact or inexact? The number of faces. Cole. Exact. We can exactly count those number of faces. Riley, tell me the mass of 6 apples. Inexact. The number of seeds in an apple, America. Exact. And the number of feet in 1 mile, is that exact or inexact, Antonio? Exact. We know that there are exactly how many feet in a mile? Anybody know off the top of your head? 5,280 feet. Yes. And what about this next one? The number of liters in 5 quarts. Why? It's 2 different measurements, or they're 2 different systems, 2 different systems. Yes, 2 different systems. So it would be inexact. The number of, it's 1.06 quarts in 1 liter. So we have that little bit of that decimal in there, so it's inexact. Yes. Because they're 2 different measurements, you know, like we have the metric system, and then we have, so because it's not exactly 1 to 1. Okay. It's about a little bit over a 1 to 1. Any other questions? All right, so something that you guys all love, significant. Oh my gosh, this thing's going to, you guys are just. Significant figures. In the AP exam, there's going to be a question. And that question, will ask you for an answer, and then they're going to expect you to know that answer should be in so many significant figures. There will be 1 point out of the possible, trying to think off the top of my head how many points are possible, but only 1 point. So if the question is worth 10 points, 1 point's going to be worth the significant figures. So what I'm going to do this year is I am going to be testing you on sig figs, but I'm just going to randomly choose 1 question. And if that question, if your answer on your test is in the correct number of sig figs, then I'm going to give you a bonus point. Okay, I'm not going to penalize you for not putting in sig figs, but I'm going to reward you if you did. And I'm just going to randomly choose 1 question. Okay? So while I like to harp on sig figs, don't stress so much about it. So rules for significant figures. When we're talking about significant figures, all non-zero numbers are significant. So non-zero number, 1, 2, 3, etc. are going to be significant. Sandwich zeros are significant. So what is a sandwich zero? A sandwich zero is one that's caught. It can't move anywhere. So 101. It's sandwiched. 100. With that decimal there, do those zeros count?
Yes.
Yes. Why? It's sandwiched. That decimal has captured it and sandwiched it. Leading zeros are never significant, so 0.003. While those zeros are sandwiched, they're leading. So the leading is going to take precedence. Okay? Trailing zeros are significant if decimal point is present. So 1, 2.0. That 0 is significant because there's a decimal present. But if we have 1, 2, 0, no decimal, that 0 is not significant. Okay? Does that make sense? And exact numbers have as many significant figures as there are needed. So if you exactly have 5, then you only have one significant figure. So let's look at these examples. 3.82 liters. Jacob, how many significant figures? 3. Emily, 24 meters. How many sig figs? 2. Mary Catherine, 0.0619 kilograms. How many sig figs? 3. Chandler,
How do I know you're this one?
2.1 times 10 to the 4th grams.
2.
2. DeMarcus, 3.4610 kilometers. 4 or 5. After that 0 comes after a decimal, a little bit after a decimal, so we are going to go with 5. And Tyler, 712,000 centimeters. 3. All right, anybody have questions on sig figs?
I do.
Yes.
If it's, for example, 5,000.00, they're all sig figs, right?
Yes. 5,000.00, those would all be significant. All right, let's take a look at measuring. Oh my gosh. So here we have a graduated cylinder. How would we record the volume? Looking at that, where should we record the volume? Or how should we? What we are looking at?
At the bottom of the curve.
At the bottom of the curve or the meniscus? So somebody looking at that, tell me, what is this measurement? 43? Is the meniscus actually, is it exactly on 3 or is it below it? 42 point maybe 5, or I would say 6 or 9. When we're measuring, we're going to look at we can go to 42, 41. We can go to the ones place, but we always go one after. So 41, 42 points, and then I'm going to look at it and say 0.9. Michael Ann might look at it and say 42.2. It's just, that's where we get that inexact from, okay? So how many sig figs did we report in this? 3. So we know 2 exactly, and the other one's a guesstimate. So Autumn, A, what would that value of A be? If you're looking at it, what would you say A is? 0.7, and we got to go 1 after that. You want to keep it at 0? Sir, all right. You've got to go 1 after it. She says it's exactly on there. So she's saying it's 0.70. You might look and see it, think it's a little bit after. So you might say it's 0.71. My last class said it was 0.71. Okay.
But then it has to be 3. Is that like why? Why do we have to do that? Yeah.
That's just the way it is. Your measurement, and then you go a little bit after because there's some uncertainty in here, right? And that uncertainty is present, so we have to take into account that uncertainty. And that's what we do when we are measuring. So what would we say B is, Chandler? 1.51. We know it's 1.5, but we don't know what that is after it. And she says it's a 1, and that's fine. And Jaden, what would you say about C? 2.89. So how many sig figs does each measurement have? How many do we have in A? 2. How many do we have in B? 3. How many do we have in C?
3.
But they all go how many decimal places?
3 decimal places.
3.
Oh, 2 decimal.
2 decimal places. They're all going 2 decimal places. Okay? Any questions on that? Let's see if I change this, what's going to happen if it changes. All right, calculating with significant figures. So when we're talking about significant figures and we're doing calculations, we always go by our least precise number. We are only as strong as our weakest link. So your answer cannot be any more precise than the least precise number to get to our answer. So this is how I like to think about it. In multiplication and division, you are going to go by your least number of sig figs. Your answer should be to the least number of sig figs. So here we have 3 sig figs. We have, in this one, we have 1, 2, 3, 4, 5 sig figs. We get that answer, what the calculator gives us. And then our answer, our overall answer, has to go 3 sig figs. So the least amount. When we're talking about addition and subtraction, what we're going to do is we are going to go the least number of decimal places. So if you have one that goes, if you're measuring and one measures to 5 decimal places and one measures only to 2 decimal places, then our answer can only go 2 decimal places. If you have here, this one doesn't measure to any decimal place, so our answer has no decimal place to it. So the least amount of decimal places. When you're doing multi-step, multiply, divide, subtract, all these things. You're going by order of operations. Your last operation is going to tell you what your significant figures are going to be in. If you added last, then you are going to go decimal places in your answer. Okay, so order of operations will dictate whether you go sig figs or decimal places. Mm-hmm. Oh my goodness. So I am going to give you about 2 minutes, probably that's more minutes than what you need, to look at these 4 examples. The calculations have already been done for you. So all I need you to do is take those answers and put them into the answer to the correct number of sig figs or decimal places. Everybody good? Okay, to the correct number of sig figs. Kaylee, what should the answer to this one here be? 0.1. You said 699. How many sig figs?
Wait, 6. I thought because they're leading there.
How many do we have here?
There's only
So there's only 3. So it would be
1, 6.
170. Okay. So the 69, the 9 rounds up the 169 to 170. Mariah, what did you get for the multiplication one?
26500.
26500. 11.3 has 3 sig figs. This is multiplication, so it's going to dictate what we're going to do. So the 6 is going to round up the 4 to a 5, and then everything else is going to be zeroed out. So we only need 3 sig figs in there. Izzy, what did you get in the addition one? 10,206.5. And the subtraction one, Michael Ann. 42.36. Any questions on those? Okay. So here are some conversions. You don't need to memorize these conversions. Some other conversions we're going to run into today are that 5,280 feet is equal to 1 mile, and that 1,600 meters is equal to 1 mile. But I do need you to know this table right here. What do I need you to know? I need you to know mega is 10 to the 6. Kilo is 10 to the 3rd. Centi is 10 to the minus 2. Milli, 10 to the minus 3. Micro, 10 to the minus 6. And nano, 10 to the minus 9. Those are the ones that you're most commonly going to see in the science world. So you just need to know that kilo, most of these you already should know. But the new ones are mega and micro and nano. So we're going to take a minute and we're going to do 5-dimensional analysis problems. I'm going to work them with you. If you have a question, let me know. Please be prepared to work the problem and give me the answer in sig figs as we go along. All right, a pencil is 7 inches long. What is its length in centimeters? So, 7 inches, 7.00 inches. What's the conversion factor from inches to centimeters? 2.54 centimeters is 1 inch. So if we put that in the calculator, we see that our inches cross each other out. They divide out. We're left with centimeters, which is good. That's what we want. And what do we get to 3 sig figs? 17.8. Speed limit on many highways is 55 mph, which means that is 55 miles per 1 hour. I want to get to kilometers per hour. So we need to convert miles to kilometers. So how many, so we can go directly to miles, or we can go directly, or from miles to kilometers, or we can go directly to kilometers. Which one y'all want to do? All right, let's go to, meters. Meters and then kilometers. All right, so what's the conversion for meters to miles? 1,600 meters, and that is in 1 mile. So we are in meters per hour. So how are we going to get to kilometers per hour? What's the conversion factor from meters to kilometers? 1 meter per 1,000, or 1 kilometer per 1,000 meters. What do you get? To 2 sig figs. 88. Questions? A Japanese car is advertised as having 15 kilometers per 1 liter. We go by miles per gallon. So we need to convert this and figure out how many miles per gallon that is. So we have 2 conversion factors we're having to do here. So first of all, how many miles per kilometer? $1.6? Oops, I put that in the wrong spot. 1 mile per 1.6 kilometers. We are in miles per liters, and we need to get to gallons. So, how many liters in a quart? Anybody remember? 106? 1.06? Hello? Okay. Ruthie, to Miss Garrett's office for your parking permit. So for every 1 liter, there is 1.06 quarts. Yeah, you need to take it. And there is 4 quarts per gallon. So put that in your calculator and get it to 2 sig figs for me. 35 miles per gallon. So this car will get 35 miles per gallon. Where's the bell ringing?
201.
Okay. Yes.
How come you have to go to meters to quarts and gallons? I think I just go straight to gallons.
You could probably go straight to gallons if you wanted to. Yeah. I was just taking the long way around. Okay, let's do one more. Let's do number 10. The density of a concentrated sulfuric acid is 1.84 grams per milliliter. So we know that 1.84 grams, for every 1.84 grams of sulfuric acid, it's going to be 1 milliliter. It's going to have a volume of 1 milliliter. Concentrated sulfuric acid is 95% pure. So what is the volume of concentrated sulfuric acid if it contains 100 grams? So we need to know, of this, how much of it is actually sulfuric acid. Okay? So we know that it's 95%, so we're going to put that into decimal. And we know that 1.84 grams. So when we multiply that, we know that in 95%, there is actually 1.75 grams of sulfuric acid per every milliliter. So if I gave you 100 grams of pure sulfuric acid, what would that volume be? Well, right here, is our conversion factor. So we know that in 1 milliliter, there is 1.75 grams. And how many grams have I given you? 100. So I want you to tell me what that volume would be to 3 sig figs. Because that should probably be a decimal right there. 100 points exactly.
Why is it not 1.7?
Hmm?
Why is it up top? Why did you run it?
Because remember we always go with our final amount. It's the sig figs that we're going to go by.
Oh.
So we still have 100 grams, so it's going to be 57.1 milliliters. When you're talking about sig figs, you always go to your question, and you're going to go by whatever your numbers you're using in your question for your sig figs. Constants, you do not use your constants to find your sig figs, amount of sig figs. Are there any questions?